Welcome back to the deep dive. If you are tracking the bleeding edge of generative AI, particularly video, you know the story. Qualities are getting amazing, but the compute cost, that's the real monster. Especially high resolution stuff like 4K. Inference latency just balloons, right? It feels like you need a whole server farm. So today, we're diving into a paper that might just, reset the whole efficiency game. It's a framework for speeding up existing video diffusion models, big time. And the kicker, they claim it doesn't just cut compute time, but it does it while keeping, or sometimes even improving, the quality. So our mission today is to unpack how they pulled off these, frankly, staggering gains.
That's right. The paper is DC-VideoGen, Efficient Video Generation with Deep Compression Video Autoencoder. It's a really solid piece of work from NVIDIA and some collaborators. And hey, for anyone needing the quick version, maybe for your stand-up meeting, here's the 1-minute rundown. So DC-VideoGen, it's essentially a post-training speed-up kit. You take a big pre-trained video model, bolt this on with some lightweight fine-tuning, and bam, faster inference. It hinges on two main ideas. First, a new kind of autoencoder, the Deep Compression Video Autoencoder, or DC-AV. This thing uses a neat trick called chunk causality for better compression and quality. Second, there's the adaptation strategy, AE Adapt V. This is how they get the big pre-trained model to understand the new super compressed data from the DC-AEV without, losing its mind. And the results, well, they're pretty wild. Up to 14.8 times faster inference. They generated 4K video that's 2160 by 3840 on just one H100 GPU. And maybe even crazier, accelerating a huge model like 2.114b. It took them only 10 H100 GPU days. That's a 230x cost reduction compared to the original training. Huge for accessibility.
Wow, okay. 10 H100 days to accelerate a 14 billion parameter model. That's seriously efficient. And like you said, it all starts with tackling that core compute bottleneck. Let's dig into that first.
Yeah, you got to remember where the work happens in these models. Things like VO, Cling, they often use diffusion transformers, DITs. And inference means crunching through just a massive sequence of latent tokens.
Yeah.
The compressed representation of the video.
Yeah.
More tokens, more compute, more time. Simple as that.
And the VAE, the video autoencoder, that's what determines how many tokens you end up with, right? It does the compression.
Exactly. And the standard VAEs out there, they give you okay compression, maybe 8x spatially, 4x temporally. Multiply that out, it's a compression ratio of 48.
Which sounds decent, but
it's not enough. Not when you're aiming for really high resolutions of really long videos, like hundreds of frames. That 48x just doesn't cut the latency down enough to be practical for many people.
Right. So the obvious next step seems like, well, just compress more, squeeze it down further. But that usually breaks things, doesn't it?
It really does. That's where the first big innovation comes in. The Deep Compression Video Autoencoder, DC-AEV.
Okay, so how deep are we talking? And what's the usual problem with going that deep?
They push it way further. We're talking 32x, even 64x spatial compression, plus that 4x temporal. That massively shrinks the number of tokens the main diffusion model has to deal with.
64x spatial? Wow. Why is that specific level so tough usually?
It comes down to a trade-off in existing VAE designs. You've basically got two main types. First, causal VAEs. They only look at past frames to reconstruct the current one.
Makes sense for video.
Yeah, it generalizes really well to long videos because it just processes sequentially. But the downside is if you try to compress really hard, the reconstruction quality tanks. It just doesn't have enough information looking only backward.
Okay, so what's the other type?
Non-causal VAEs. These look both backward and forward in time, bidirectional context.
Ah, so they have more information to work with.
Exactly, which means they can handle much deeper compression and still get good reconstruction quality.
Wow. There's always a but.
Right. They generalize poorly to longer videos. Because they need future frames, you often end up having to process the video in chunks, maybe overlap them, blend them.
And that introduces artifacts, like weird flickering or seams.
Precisely. You get temporal flickering, boundary blurring, stuff like that. It just doesn't look smooth or coherent over longer durations.
So it's this annoying trade-off. Good generalization or good quality under deep compression. How does DC-AEV's chunk causal idea get around this?
It's a clever hybrid approach.
Oh.
They split the video into fixed-size chunks. Their tests found 40 frames was kind of the sweet spot.
40 frames. Okay, why 40?
Seems like it gives enough local context for good quality, but isn't so large it hurts efficiency. An empirical sweet spot found through ablation studies.
Gotcha. So chunks of 40 frames, then what?
Within each 40-frame chunk, they use that bidirectional flow, looking backward and forward inside the chunk. That gives them the high reconstruction quality, like the non-causal models.
Ah, but only within the chunk.
Yes. And then, across the chunks, they enforce strict causal flow. So chunk 2 can use info from chunk 1, chunk 3 from chunk 2, and so on. But chunk 2 cannot see into chunk 3.
I see. So you get the local quality boost from looking ahead a bit, but maintain the overall forward-only progression needed for long videos.
You got it. It keeps the generalization ability of causal models while getting the reconstruction fidelity of non-causal ones, specifically under that deep compression.
Okay, that sounds elegant. Do the numbers back it up? How does it compare to other VAEs when pushed to these high compression rates?
They show this in Table 1. DC-AEV hits a PSNR, that's peak signal-to-noise ratio, a quality metric of 37.37, even at a 96x overall compression ratio.
96x?
Yeah, and that score significantly beats both state-of-the-art causal and non-causal VAEs under those same harsh compression settings. It really validates the chunk causal design.
Okay, fantastic. Problem 1 solved. We can now compress video deeply without wrecking the quality, thanks to DC-AEV. But like we hinted, that creates a second problem. You've got this giant pre-trained diffusion model, like that 14 billion parameter WAN model that was trained on the old VAE's output, the less compressed stuff. Now you're feeding it this new super compact data. How do you bridge that gap? How do you teach the old model this new language without starting from scratch?
That's exactly the challenge. You've got billions of parameters in those main DI key blocks holding all that learned knowledge about how video works.
Yeah.
You absolutely do not want to retrain that from zero. It's way too expensive.
Right, so let's look at what doesn't work first. They tried a simple approach, right? The turtle approach, they called it. What did they try, and why did it fail so spectacularly?
So when you swap out the VAE, the input and output layers connecting to the main DIT blocks need to change. These are the patch embedders at the input and the output head at the output.
Okay, the layers that translate between the VAE's world and the DIT's world.
Exactly. The patch embedder takes the VAE's compressed tensor and turns it into the embedding vectors the DIT understands. The output head takes the DIT's final vector output and translates it back into a tensor for the VAE decoder.
So the simple idea was just freeze the giant DIT and train only these new input-output layers.
Yeah. Initialize the new patch embedder and output head randomly, freeze everything else, and just fine-tune those two small components.
And disaster.
Total disaster. The paper shows the output just collapsed into random noise after only about 20,000 training steps.
Why? What went wrong?
It's because of what they call the embedding space gap. The randomly initialized patch embedder was just spitting out garbage vectors, essentially. It had no idea how to map the new compressed latent space into the semantic space the frozen DIT was expecting.
So the DIT was getting meaningless input and couldn't make sense of it?
Precisely. The whole training process just fell apart.
Okay, so that brings us to the rocket approach, the AE Adapt V strategy. This is designed specifically to avoid that embedding space gap, right? Walk us through stage 1, the video embedding space alignment.
Right, this is the crucial setup phase. It happens before you even try to do the main fine-tuning. It's got 2 steps. First, patch embedder alignment.
How do you align it if you don't want to touch the DIT?
They get clever. They take the old patch embedder from the original base model, the one that does understand the DK keys language, and they freeze it. They use it as a teacher. Then they train the new patch embedder. Its job is to take the new deeply compressed input from the DC-AEV and produce an embedding vector that's as close as possible using mean squared error loss, MSE loss, to what the old embedder would have produced for a similar but less compressed input.
Ah, okay. So you're essentially forcing the new embedder to learn the target language of the DIT by mimicking the old embedder on downsample data. Brilliant.
It is pretty smart. And the ablation studies in the paper show this step, the patch embedder alignment, is absolutely the most critical piece for making the whole adaptation work smoothly.
Okay, so embedder aligned. What's the second part of stage 1?
Output head alignment. Now that the input side is speaking the right language, they jointly fine-tune this newly aligned patch embedder and the new output head. They use the standard diffusion loss for this, but crucially, the main DIT blocks are still frozen solid.
And this alignment stage is quick.
Yeah, only about 4,000 steps according to the paper. Super fast compared to full training.
Wow. Okay, so stage 1 basically preps the input and output layers to communicate properly with the frozen core. What happens in stage 2?
Stage 2 is the final polish. End-to-end fine-tuning using LoRa. Now they finally unfreeze the main DIT blocks, but instead of fully fine-tuning all billion parameters.
Which would still be expensive.
Right. They use low-rank adaptation, or LoRa. This involves inserting much smaller, low-rank matrices into the DIT layers and only training those.
Why LoRa instead of just fine-tuning everything?
2 key reasons from their findings. 1, LoRa involves far fewer trainable parameters, so it's much more efficient. 2, and this is important, they actually got better results, higher VBench scores, using LoRa compared to full fine-tuning.
Interesting. So LoRa is better at preserving the original knowledge.
It seems that way. It suggests LoRa is less prone to disrupting the complex knowledge already baked into that massive pre-trained model while still adapting it effectively to the new compressed space.
Makes sense. Okay, one quick detail. What about image-to-video models? They often have a static image as a starting condition. How does that fit with this chunk causal structure that expects, well, time?
Good question. They had a neat little workaround for that. Since the model expects chunks of frames, they just take the input static image, replicate it 4 times, and then append some blank frames to make up the first 40-frame chunk.
Ah, so you just feed it the same image a few times to satisfy the chunk structure.
Pretty much.
Yeah.
It lets the I2V models use the exact same efficient DC-AEV and adaptation process without needing major changes.
All right, let's get down to the payoff then. We've got the deep compression with DC-AEV and the smart adaptation with AE-AdaptV. Putting it all together, what do the benchmarks actually show? Let's talk brass tacks.
Okay, the numbers really do tell the story here. Let's circle back to that training cost first. Accelerating WAN 2.114b, that massive model.
Yeah, 10 H100 GPU days.
Right. Compared to the estimated 2,300 GPU days to train the base model itself. That's the 230x reduction in compute needed just for the acceleration part.
That is just game-changing for accessibility. Suddenly, taking a state-of-the-art foundation model and making it run fast isn't just for the giant labs anymore.
Absolutely. It opens doors for smaller teams, university labs, even efficient startups. Now let's talk inference speed, what the end user actually experiences.
Yeah, the 14.8x number, where'd that come from?
That was for generating high-resolution video, 2160 by 340 pixels. On a single H100, the original model took about 375 minutes, over 6 hours.
Oh.
Yeah. With DC-VideoGen applied, that dropped to roughly 25 minutes. That's the 14.8x speedup. Huge difference.
And for longer videos?
Similar story. For generating 640 frames at a lower resolution, the speedup was 14.2x. Latency dropped from almost 5 hours down to about 21 minutes.
Okay, speed is fantastic. But the inevitable question, what about quality? Did they trade away visual fidelity to get that speed?
That's the most surprising part,
Yeah.
maybe. No, they didn't. In fact, in some cases, the quality actually improved slightly, according to the V-benchmark.
Improved? How?
Well, for text-to-video, the accelerated DC-VideoGen version of WAN 2.114b scored 84.83 on VBench. The original base model scored 83.73.
So it got faster and slightly better on that metric.
Yep. It suggests the AE-AdaptV process, especially with LoRa, might even act as a kind of regularizer or refinement step, preserving and potentially enhancing the core capabilities.
So bottom line, when compared to other leading models,
The DC-VideoGen accelerated models ended up with both the highest VBench scores and the lowest inference latencies among the competitors they tested against, like Ambi-1, Step Video, Hanwhan Video, best of both worlds, essentially.
this really feels like a significant step then. It shows you don't necessarily have to choose between efficiency and quality.
Exactly. It makes high-res, high-fidelity video generation on, reasonably accessible hardware, a single GPU actually practical. That's a big deal for deployment and research. Now, the authors are upfront about limitations, of course, since it's a post-training framework.
Right, it can only be as good as the model it starts with.
Precisely. If your base model isn't great, DC-VideoGen isn't magic, it won't fix fundamental flaws. It accelerates what's already there. But their clear future direction is pushing this further, especially for generating even longer videos, building on this efficient foundation.
So wrapping this up, it seems DC-VideoGen offers a powerful, practical path to making cutting-edge video models vastly more efficient. Which brings us to the final thought for you, our listeners. We've seen acceleration methods like this dramatically slash the cost and time for inference, especially for demanding tasks like 4K video. If making these huge models run fast becomes this much cheaper and easier, how quickly do you think that practical barrier to entry is going to drop? How soon before independent researchers or smaller companies can realistically deploy models that were, just recently, the exclusive domain of hyperscalers? Something to think about.